It always lags when I start recording. Okay, so let's keep talking about applications of derivatives from last time. So the last thing that we discussed was this tangent line approximation for, if there's, and my pen is having a terrible day. We discussed how if you have a complicated function, it's often, what are you doing? Alright, I'm just going to unplug and replug my pen and talk until that gets fixed. But we discussed that if you have a complicated function and you're trying to evaluate a point near a known value, like Feynman's little anecdote about the cube root, often it's much easier to use a tangent line approximation. So this is incredibly common. This is sometimes called a linearization. And especially in engineering, chemical engineering, for instance, if you look at chemical engineering courses on MIT OpenCourseWare, much of it is just solving linearized differential equations in MATLAB because we're really good at lines. We as humans are very good at lines and very bad at things that are not lines. So this is incredibly common. I want to recap that first. Then I want to talk a bit more about optimization. I think we've proved most of what we need about local maxes and mins, and then we can start doing a few problems after that. I mean, the next couple sessions I just want to do kind of an orgy of optimization problems because I think these are really nice and crunchy and give you a good intuition.
Are you recording?
Yeah, I started a minute ago.
Okay.
Yes, it says recording. Good. Thank you for checking, though. And then last, this will be our first actual algorithm. So I think I might, on a daily challenge, ask you to implement this in Python. So I'll tell you more about what this algorithm actually is. But this is the first time we'll have a serious numerical algorithm which is used in real applications to solve, hard problems that people care about. So I think there might be a couple slides missing. Yeah, I wanted to add some slides, but then I didn't have time today, so I might have to improvise. But this is at least the sketch of what we're going to do. So, okay, thoughts or questions on the roadmap or big picture?
Are you suggesting that at some point you are going to be having a Python program due?
I think so. Why? Is that bad?
Sounds fun.
Yeah, I think it's very useful. I mean, you asked a question on Slack a while back about how does a computer take a derivative without dividing by 0, right? This f of x minus f of a over x minus a or something, limit as x goes to a. This is one way to write the derivative instead of h, but whatever. Yeah, you said how does a computer compute this without dividing by 0? Because you want to make x as close to a as possible so the bottom gets huge. And this is a very interesting question. This is something which comes into the field of so-called numerical differentiation. And the punchline is that, yeah, there's a lot of things you need to take into account. There's floating point overflow error because you have to ask, is there going to be some rounding issue if I take x very close to a? So often people use these interesting techniques where they pick like 5 points. For some reason, I think 5 is the most common, where they pick 5 points nearby and try to approximate the derivative using this 5-point approximation. Or if you go into NumPy, I don't know if you use NumPy in Python, but it's one of the more common numerical libraries. There's this np.gradient. Gradient is a numerical derivative, and np.gradient will approximate the derivative in a way which is pretty robust against this sort of overflow error from dividing by 0. But gradient assumes that your function is C3. Like if you open up the NumPy documentation, it'll be like, here's the algorithm we use. You need a C3 function, so it has to have 3 continuous derivatives. And then you worry, okay, what if my function isn't C3? Is this going to be a good approximation to the derivative? So I'm not telling you anything of content here. I'm just trying to give you a flavor for the difficulties that arise in trying to do calculus on a computer. It's much harder than you would think. So I'll tell you a little bit more about that later today, but then I think I'm going to offload much of the work onto you in writing an interesting implementation. Good. Okay, interesting thoughts. Other questions?
I do not have any thoughts.
All right, let's recap then. So this will be just one slide on what we did last time. So we discussed again this tangent line approximation. So the idea was that if you have a function f, say, here's an example which is oddly pixelated. The example is f of x equals x squared, so you want to approximate, say, a parabola. and maybe, maybe you don't want to actually compute the value exactly, you want to approximate it. So one technique for doing this is going to a known value, like x equals 1, and then finding the tangent line to the graph about that point, and then arguing, my pen is bad, but then you can argue that for points on the graph which are near this point that you're expanding about, the value on the tangent line is good enough. It's a reasonable approximation to the value of the actual graph. So this is what we saw last time with several examples, like e to the x or sine x or whatever. And in every case, we just use this, point slope form or whatever. This is just algebra. I don't know, what is it, y minus y1 equals m times x minus x1 or some shit, some magic words that have been pounded into your head since 7th grade or something. And of course you can just rewrite this in the form y equals, well, I'll write the y1 first, y equals y1 plus m times x minus x1. And then of course this is exactly what I've written down. You just notice the derivative, f prime, is paired up because that's the slope. F of a is the y1, x minus a is the x1. So I'm just trying to get into this formula. You don't need to memorize this because you already know it. If you need to figure out the tangent line approximation, just remember point slope and then put in the derivative for the slope of the line. It's nothing new. It's just something you know in an unfamiliar form. Okay, so that's what we saw last time. Now, as a quick review challenge, I will ask you one of the more common approximations in physics. This came up roughly 10,000 times in doing my physics GRE prep course over the summer. So suppose you have this function f of x equals 1 plus x raised to the power n, where often n is an integer, but really n can be any real number. So I will ask you, if you want to approximate this function for x small, which means x is near 0, x is approximately 0, what should we do to get an approximation to this function?
I believe that we can start by letting x equal 0 for means of approximation. And to remember the form where, I think, as you said, there is a way to memorize this.
Yes, I'm against memorization. I'm all for rederiving in the moment. So how do you rederive this in the moment? You remember y equals y1 plus m times x minus x1. You ask what's m? M is the derivative. What's y1? It's the height at the point you're expanding around. And then what's x1? Well, it's the value 0 in the case you just told me that you're expanding x around. So f of x is f of a, the y1, plus m, f prime of a, times x minus x1. Good. All right, so what should I write here to use that?
So we're going to have that this is going to be at f of assuming x is about 0. So that's going to be about, let me think, 1 to the power of n, which is still 1 plus, let me think, about the derivative of this. This is going to be by the chain rule, n times 1 plus x to the power of n minus 1. I almost forgot.
But remember, we evaluated...
right, 1 plus 0 to the power of
Good.
n minus 1.
What else?
It's going to result in... Yeah, that's going to be times... Thinking again. I feel like it's something super short, and...
Remember, this is in the point slope form. This is the x minus x1, where x1 is the point you're expanding around, and we're assuming x is close to 0. Right?
This is going to be times 0 minus... What? Is it going to be times 0 minus whatever small x is?
Or x minus 0, right? Yeah, other way. But it's x minus the point you're expanding around, so x1 is the 0, because we're expanding around 0. Or we're approximating around 0. You keep hearing me slip into this language of calling it expanding, because I'm thinking of Taylor expansions, which we'll learn later. But good. Okay, so let's simplify this. So as you started to say when I cut you off, you can evaluate this. So then what does this end up as?
So this is going to be 1 plus n times x.
Yeah, very
Plus
good.
n.
N times x, because the x minus 0 is nothing. So I'll rewrite, well, whatever, it's an approximation, so I won't write equals, but good. This is one of the things that, I mean, you can rederive it in 30 seconds once you've seen this, but it's almost worth memorizing just because this comes up so frequently. If you ever have some small number, especially in physics, a dimensionless quantity, and f of x, which is 1 plus that small number raised to some power, you can just almost remember the mantra that 1 plus x to the n is 1 plus nx for small x. And it will save you a lot of time. And we'll see an example in a moment for where this shows up in a physical context, because often in physics, I mean, you want to approximate things by identifying some quantity which is small enough to neglect, like, I don't know, air resistance or something small. But before we do that, questions or thoughts on this challenge?
I do not have any questions or thoughts.
Good, okay. All right, so I think I have the solution here. Yes, good. That's a typo, n minus 1, not n minus 2. But indeed, yes, the derivative at 0 is n times something which is 1, which is n. So as you told me, f of x is approximately f of 0, which is 1, plus the derivative, which is n times x. So 1 plus x to the n is roughly 1 plus nx. Okay, why is this useful? Alright, so let's see an example from special relativity. So one of what I think is the most shocking results of special relativity is that there is no universal notion of time. Time is different for different people. So if you have a clock which is moving, you put a clock on a jet plane, time passes more slowly on that clock. A moving clock ticks more slowly. And the equation for the time which elapses on the moving clock and the time which elapses on a stationary clock is given by this. T prime is the time on the moving clock, equals t, the time on the stationary clock, divided by the square root of 1 minus v squared over c squared. So what is this? V is the speed of the moving clock, or the velocity, if you will, of the moving clock, and c is the speed of light. So 2 comments. 1, in most applications, this is very small, because most things are moving much more slowly than the speed of light. So if you divide their speed by the speed of light, you'll get a small number. Or in this case, we'll do something where v over c is a half, so the square of that is a quarter, and a quarter is reasonably small. So that's the first comment. The second comment, which I apologize for because there's not much I can do about this because it's just a common notation. Often in physics, when you have 2 different quantities that you want to use the same letter for, but they're different, like say time in one frame and then time in another frame, you will put this prime mark, which we've been using for a derivative before, to indicate that one time is different from the other time, so time in another frame. So just to emphasize, this is not a derivative. This is not the derivative of time with respect to something. This prime is totally different. Sometimes prime means derivative, and sometimes prime just means some different value of that variable. I realize it's kind of confusing, but there's nothing I can do about it. They're just both very, very common. Sometimes prime means different, sometimes prime means derivative, so whatever. Okay, so with that said, different time equals time divided by root of 1 minus a small thing. I will ask you, how can we use the result from the previous slide, which again I remind you involved 1 plus something small raised to a power, how can we use that to approximate t prime if t is, say, 1 second, by expanding this thing on the right side somehow?
So I'm thinking before all else, I don't think that for what we are interested in, v squared over c squared is small. Oh my god. I'm looking ahead at the 50% of the speed of light.
Yeah, I mean, it's small enough. If v over c is a half, then v squared over c squared is a quarter. And you asked last time how small is small enough for like that sine of x is approximately x. I think my answer was like 0.2 or 0.3. If it's less than 0.3, then your error will be less than 10%. So you should think roughly, if you're getting a rough estimate, like 0.3 is small enough. So a quarter is definitely small enough.
All right. So we're going to thinking. I guess. Yeah, I guess we let v where v quote unquote equals x for our interest and the equation that we know. So I guess convert this top equation to the form 1 minus v squared over c squared quantity to the power of -1/2.
Good, so 1 minus b squared over c squared to the -1/2 all times t. Okay, so just to remind us of what we did on the previous slide, I guess, this thing would then...
Wait, is there a times t? Oh, right.
There's t upstairs, right?
Right, yeah.
Good, so now this thing is the x, because remember the previous slide was 1 plus x, so just to get the sign right, we need x to be minus v squared over c squared, and now this is what we were calling n before, right? Just to remind you. But okay, good. So how do I approximate this now?
So we saw, according to the previous slide, that this is going to be, as a whole, this entire thing to the left is going to be 1 plus nx. So we're 1 plus -1/2 x.
Good, and x is this minus v squared over c squared?
Yeah.
All times t. And, I mean, let's evaluate that. So if v over c is a quarter and t is 1 second, what happens when we plug those in?
So this is going to be, well, since t is 1, we can effectively eliminate it because we don't have to worry about it being, yeah, you know what I'm trying to say.
Yeah, good. So I'll just put 1 here. Good.
Yeah. And by fraction multiplication, we are going to have 1 plus 1/8.
Good. 1 plus 1/8. So this is, I guess, 9/8 of a second, or, I mean, I hate decimal, but just to give us a sense, 1/8 is what, 1.125 or something? So this is 1 plus 1.125 seconds. Okay, let's see if I made an arithmetic, or one of us made an okay, neither of us made an arithmetic error. Good. So as you say, the time on the moving clock, t prime, is roughly t times 1 plus v squared over twice c squared because of the 1/2 downstairs. And if v over c is a half, then this becomes 1 plus 1/8, which is 1.125 seconds. So it's interesting that even for an object moving at this appreciable fraction of the speed of light, like 50%, the time dilation, as it's called, the amount by which time ticks more slowly on the moving clock, is still pretty small. For every second that passes in the stationary frame, only 1.125 seconds pass in the moving frame. So you might say, okay, why do we ever need to take into account this sort of relativistic effect? Why does anyone care about this? And the answer is, well, no one cares about this for, say, bullets or fighter jets or things that are moving at macroscopic speeds. But in a particle accelerator, say CERN, where all of your protons are moving at 99.99% the speed of light, this becomes the dominant effect. It's incredibly important. Or if you're an astronomer and you're studying, say, cosmic rays that interact with ozone atoms in the upper atmosphere and create these muons, there's a famous effect where the muons, you would say, the muons have a very short lifetime, so they decay very quickly. And if you did not take this time dilation effect into account, you would naively say none of the muons will ever live long enough to reach the Earth's surface. They all decay far before they could reach the Earth's surface. But in fact, if you set up a muon detector at the Earth's surface, you get a lot of them. So apparently many muons are surviving to reach the Earth's surface. then you would ask, why are these muons that are so short-lived? They last for like a millionth of a second. Why are they living long enough to reach the Earth's surface? And this is the answer. The muons are moving so close of the speed of light that even though they live only a millionth or 2 millionths of a second, as measured by, my wristwatch, someone who's stationary, according to the muons, since they're moving very fast, they have a moving clock, so they, from their perspective, they live much longer, which is very strange to me. So I don't know if you've ever read Ender's Game, but there's a character who has, in that novel, without giving anything away, a character who has lived for what seems like hundreds of years to other characters living on Earth, but that's just because they put him on a spaceship going at 99% the speed of light for far away and then to come back. So from his perspective, he feels like he's just an ordinary, 50-year-old man, but everyone else thinks he's hundreds of years old. So anyway, this is a bit of a rant, but just to show you that, this Taylor expansion is a useful approximation, and it appears in both actual science and in science fiction. Good. Thoughts on this?
Does that mean you could stick an atom of I'm thinking, huge atoms that would decay in fractions of a second? Could you place those in a particle accelerator and make it easier to study by having them moving quickly?
They would live longer. Yeah, if you had, say, a radioactive atom and put it in a particle accelerator, and you, I don't know, if you could still study the atom when it's moving very quickly away from you, which, I don't know, if you want to, if you want to scatter photons off of it, then maybe that's kind of hard, but if you just want to measure its decay products or something, then certainly you could still do that if it's moving very quickly. Then yes, you could absolutely extend the lifetime of a short-lived radioactive nucleus by moving it very fast, close to the speed of light. Good. It's a very interesting comment, actually. I don't know if anyone has ever done that, but it's an interesting idea.
The more you think, I don't know.
Thinking is good. Other thoughts?
Nope.
Nope. Okay. All right, onwards then. All right, so I want to wrap up optimization and then do a few problems. So let's just say a few words about what we've done already in terms of optimization. So in the last couple meetings, we've been kind of building this utility belts, or this toolkit, if you will, of different ways to use derivatives of a function f to understand the graph of f itself. So we proved that the sign of the derivative controls whether f is increasing or decreasing. For instance, we proved if f prime is positive, strictly positive, then f is strictly increasing, and so forth. We proved two times ago, whenever it was, that the second derivative controls the convexity or concavity. So if f double prime is positive, then f opens up, and if f double prime is negative, then f opens down, which is called concave. We saw these critical points. So often these critical points of a function where the derivative is horizontal, these will sometimes, but not always, be local extrema. Why do I say sometimes? Well, a counterexample is something like the graph of x cubed. And of course the derivative of this is x squared, so x squared has a root at x equals 0, so there's tangent line f prime equals 0 at x equals 0, but clearly by looking at this graph, x equals 0 is not a maximum or a minimum, right? It's just what we sometimes call a saddle point, so to speak. It looks like a saddle or a Pringle. So these critical points are sometimes, but not always, local maxes and mins. And then we had this this thing that you worked on today for the daily challenge that enumerated these three possible cases, more or less, where a global max on an interval occurs either where the derivative is 0, or at an endpoint, or a place where the derivative doesn't exist. Okay, so that's what we have so far. Using that, just a quick question. If I have shown you these two different plots, one function is in red and one is in the dotted blue, and I tell you that one of these two plots is a function f, and the other plot is the derivative of that function, f prime. How could you tell which is which between these two?
I believe that the red is f prime
Man, okay, that was fast. How did you know?
because it would seem that I'm just looking at the right side, but where the derivative, well, where the derivative equals 0 is where the blue dotted line has 0 slope.
Yeah, good. Okay. So this guy, the red curve has a root here, and at that point the blue curve has a horizontal tangent. Yeah, so that's a dead giveaway. That means indeed that blue is f, and this red should be f prime. Okay, that's yeah, all right. One other thing that you have well, you've probably noticed since you were playing around Desmos, and you might conjecture based on looking at this, is you could say,
Yeah.
what did you say? Oh yeah, know that
What's
Desmos.
going on with the right side? I mean, left side.
What's going on here? I mean, I think it matches our intuition, right? Here, the red curve,
Oh, yeah.
0. This guy is a horizontal tangent. Here, the red curve is very negative, and this guy has a negative slope. So I think the left side pretty much matches our intuition as well. But the thing I was going to emphasize is that you might have come up with this idea that, like, well, it's often the case, that's a bad color, I guess, but green. There we go. So you might have noticed it's often the case that places where the derivative, as you've identified the red curve f prime, places where the derivative vanish are often local maxes and local mins. But you might have wondered, is there a way quickly to determine whether a root of the derivative corresponds to a local max or a local min? How do you know which is which, right? In both of these cases, the derivative is 0, but here it's a local max and here it's a local min. And you might have thought, well, why don't we look at the slope of the first derivative, which is, of course, the sine of the second derivative, and you would say, well, at this point, the derivative is decreasing, so the second derivative is negative, and that means the original function opens down. So if there's a flat tangent and you open down, you got to be a local max. Or correspondingly over here, if we say, okay, the derivative is 0, but the derivative is increasing. So that means the second derivative is positive, and then you might conjecture, well, does that always mean that since the original function has a flat tangent, but it also opens up, that you must be at a local min? It's a pretty reasonable guess. We'll see shortly that it mostly works out. That's the last thing in the toolkit that we want to develop. So, just to reiterate the intuition I just gave, if the second derivative is controlling whether you open up or open down, you might think if you look at a point where the first derivative is 0, we can use the second derivative to decide whether it's a local max or a local min. So let me just put a bit more flesh on that. There's two directions here that we're conjecturing, more or less. So the first conjecture is the statement that if the first derivative is 0, but the second derivative is positive, are we always guaranteed that that point is a local minimum? Or, you know, the same statement with this being replaced with negative and this being replaced with maximum, but I won't state it twice. So this is roughly that, you know, second derivative implies max versus min. And as we'll prove in a moment, the answer to that question is yes. But the second, you know, the converse of that statement, the other thing you might conjecture is, does the relationship also go the other way? Which is to say, if, you know, the second derivative exists and you are at a local minimum, is it guaranteed that the second derivative is strictly positive? So this is, you know, max versus min implies the sine of f double prime. This is the other direction. So as we'll see in a couple slides, the answer to this question is actually no, but it's almost true with a small modification. So I want to distinguish between these two because often it's easy to become confused between a statement and its converse. This is a recurring theme, I think, in, you know, both in our meetings and in mathematics generally, because just because one statement implies another doesn't mean the second statement implies the first, right? I don't know, if you are a gay man, then you are attracted to men. if you are attracted to men, it does not imply that you are a gay man, because you could also be an androphilic woman, right? So it doesn't, the converse statement is not actually true. Attracted to man. I don't know why I didn't pluralize that. The more common way of phrasing this is that if you are a man, you are necessarily a human. If you are a human, you are not necessarily a man. It's not always true that if one thing implies another, that the second thing implies the first. So we see that here. Okay, possibly a strange example, but before I do the proof of the first statement, thoughts or questions on this second derivative comment?
I do not have any thoughts or questions.
It sounded very decisive. Okay. Good. Let's prove the first one. This is sometimes called the second derivative test. Okay, so here's the theorem. We suppose that the first derivative is 0, so we have a horizontal tangent. As we've seen, that could, look like any of these things. We also assume that the second derivative exists and it's positive. So if the second derivative exists and is positive, then the conclusion is that f has a local minimum at a. So that's this case, the first case. There's a second conclusion, which is that if instead the second derivative is negative, which is this third case, then f has a local maximum at a. So this was number 1 on the previous slide, the first conjecture. And I'll prove it in a moment, but the idea of the proof is pretty simple. It's just going to say that, we're going to, for instance, just do the f double prime positive case. And what we'll do is say, okay, well, suppose f double prime is positive at the point where the derivative vanishes, and we're going to kind of cut this in half and try to find some interval, maybe a minus delta to a, and then a second interval a to a plus delta. I'm just going to find a small interval and try to show that under the assumptions of this theorem, we have that f prime is negative on this one. F prime is negative on some interval to the left, and f prime is positive on some interval to the right. So why does this prove what we want? Well, if f prime is negative on some interval to the left and positive on some interval to the right, then that means the function is decreasing, strictly decreasing, on some interval a minus delta to delta. And remember, strictly decreasing means that, well, I'll just remind us of what we're saying. So strictly decreasing means that if you have two numbers on the interval c less than d, then f of d, the one further to the right, is always going to be strictly less than f of c. So this is the definition of strictly decreasing. So if we can show that the function is strictly decreasing on some interval to the left of a, and similarly strictly increasing on some interval to the right of a, that means that by definition on that interval, all of the points on the left side are going to be greater than f of a, and all of the points on the right side are also going to be greater than f of a, which means that a is a local minimum by our definition of local minimum. So if we can prove this statement, we have proved the theorem. And I'll do that in a moment. But before doing that, questions about the idea or the statement of the theorem?
I do not have any questions.
Cool. Okay, let's prove it then. Okay, here's the proof. So remember the setup again. So it's important that f prime is 0 at this point. So if f prime is 0, all we do is write down the definition of the second derivative. As you said last time, I think, the definition is as the derivative of the derivative. So it's the limit as h goes to 0 of the derivative f prime of a plus h minus f prime of a over h. And this is all at this point a we're interested in. As I just highlighted, we have assumed the first derivative is 0 at this point. So the second piece in the numerator vanishes. This is 0. So I've just rewritten it on this line here, rewriting the limit as h goes to 0 with that second term gone. F prime of a is 0. Okay, so that was using our first assumption. We've used this assumption that the derivative is 0. Now I'm going to prove the claim in the case where the second derivative is positive. So let's go back over here. Here's our expression for the second derivative. Now assume that that expression is positive. Okay, so we're assuming this whole thing is greater than 0. Now there's two cases, because as h goes to 0, there's the case where h goes to 0 from above, where h is positive, and there's the case where h goes to 0 from below, where h is negative. The point is that this fraction has to be positive in both of those cases. So in the case where h is going to 0 from above, that's a small positive h. If this fraction is positive and the denominator is positive, then the numerator is also positive, right? Positive divided by positive. So in that case, the derivative f prime at that point, a plus h, must be positive. Okay, fine. The second case is h going to 0 from below, so if h is small and negative, it's still true that the ratio of these two must be positive, but if the denominator is negative, that means the numerator must also be negative, because negative divided by negative is positive. So when, negative h, we must have that the numerator, f prime at a plus h, is negative for small h. So negative h and positive h. Okay, but actually that's just what I sketched a moment ago. So the picture on the previous slide was we were trying to show that we could find some intervals a minus delta and a plus delta with the properties that f is increasing to the right of a. Increasing means f prime is positive over here. And decreasing in some interval to the left of a, that means f prime is negative over here. And we've just done that because now we've shown that for small enough h, for small positive h, that is, that's the right side, the a plus delta, here the derivative is positive, so the function is increasing. And in the second case, when small negative h, that's the left side, here we've shown the derivative is negative. So this proof furnishes us with an argument for why the function must be strictly decreasing on some kind of tiny interval to the left of a and strictly increasing on some tiny interval to the right of a, which guarantees that a is a local minimum. Good. I won't repeat the proof in the other case. If the second derivative is negative, just say all of the same words I just said, but replace greater than 0 with less than 0 and positive with negative and so forth, and you'll get the same result. It's kind of a trivial exercise, but anyway, so this is what we wanted. This is number 1, that if the first derivative is 0 and the second derivative is positive, we are guaranteed to be at a local minimum. That's the point. Okay, thoughts on this?
I do not have any thoughts or questions. This is simple enough.
Good, okay. So now you ask, well, why doesn't it go the other way? Right, this seems like it's such an obvious relationship. Why wouldn't the existence of a local minimum guarantee the second derivative is positive? What breaks? And to show you what breaks, I invite you to consider the familiar function f of x equals x to the power 4. Okay, why is that a good counterexample? Well, x to the power 4 looks a lot like a parabola, except with kind of a different rate of change near the origin. So this thing clearly has a local minimum at the origin. And the claim we're testing is, well, I thought every local minimum with a first derivative 0 has to have a positive second derivative. But the second derivative, f double prime of x, as you can verify by using the power rule twice, where you pull down a 4, then you pull down a 3, so this would be 12x squared. So it is not true, which is, I don't know how to write this, not, maybe I should use a different color, it's not positive at the origin. So there's something fishy going on here, because we found that if you know that you have a positive second derivative when the first derivative is 0, you have to be at a local minimum. But this x to the 4th business gives us an example where the second derivative is not positive, but we still have a local minimum. Right, so apparently it doesn't go the other way. The converse isn't true. But you might guess, okay, well, that's kind of a stupid example, because the second derivative is almost positive, it's just 0, right? What if we just changed the claim so that it could be greater than or equal to 0? Would that be true? Does that fix the problem? Or are there more counterexamples? And in fact, that does fix the problem. So this is the only kind of pathology, the only thing that goes wrong with that claim. So I call this a partial converse. So here's the partial converse. If you assume the second derivative exists, and you also assume that the function has a local minimum at a, so like x to the fourth or whatever, then the second derivative must be greater than or equal to 0. As you've just seen, we really need that or equal to, because x to the power 4 gives a counterexample if we omit the or equal to. And the same thing is true if you flip the sign. If it's a local max, then less than or equal to 0. Okay, why is this true? The proof is very easy. It actually just uses the theorem. This is an interesting theorem because it almost proves a converse to itself, right? So this theorem is telling us that, if the first derivative vanishes, you get a local max or a local min, depending on whether the thing is greater than 0 or less than 0. How do we use that to prove the converse? Okay, well, we'll do a proof by contradiction, right? So I'll, again, do only the local minimum case. Okay, so here's the proof. So suppose f has a local minimum at a, the statement of the theorem, and we've proven a while back that at every local max or min, the first derivative vanishes, right? That's fine. And now we suppose by way of contradiction that the second derivative is strictly negative. Right? Why is that good enough for contradiction? Because we're trying to prove that it has to be greater than or equal to 0. So if you put a not in front of greater than or equal to 0, that's the statement that it must be strictly less than 0. Okay, so that's what we need for a contradiction. Not greater than or equal to means less than. Okay, but the contradiction is very easy, because if we assume that the second derivative is negative, we've just proven a very nice theorem that shows that whenever the second derivative is negative and the first derivative is 0, this previous theorem tells us that f must also have a local maximum at a. So now it's a little strange because we've assumed it's a local minimum at a, but by our contradictory hypothesis, you can also prove it has a local maximum at a. The only way you can have both a local max and a local min is if the function is constant on some interval around a, right? Because local max means you are greater than or equal to everything in the interval, and local min means you are less than or equal to. So the only way you can be both greater than or equal to and less than or equal to is if you are precisely equal to. But if this guy is equal to everything in some interval, then he's constant. However, this is a contradiction, because if this guy is constant in some interval, then, well, if he's constant, of course, his first derivative vanishes, but also his second derivative vanishes. But that contradicts our hypothesis, because we assume the second derivative was strictly negative, always less than 0. So if it equals 0, then 0 is, of course, not less than 0. Okay, good. I mean, not a terribly deep proof. You do the same thing, but reversing the signs again for a local maximum. But this is the partial converse that we were interested in. So if you know it's a local max or a local min, you know up to the possibility that it's 0, up to that possibility, you know the sign of the second derivative. Okay, good. Perhaps not very deep, but thoughts or ideas related to this? Can't tell if thinking or quiet or push to talk.
Thinking.
Ah, good.
I do not have any thoughts or questions.
Okay. All right. Well, fine. So since that's the last optimization thing we need, let's do a couple problems. So the first one, this problem appears basically identically except for wording in both Art of Problem Solving and Spivak, and I think it's funny to examine the difference. So first, here is the way the problem appears in the Art of Problem Solving book. It says, Cody has a pet goat named Baroness Regina von Poffelstein, and he wants to create a rectangular grazing area for her. He only has 40 feet of fencing. What is the maximum area he can enclose? Now, I find this almost insulting to read. I guess they're pandering to whatever the advanced 7th and 8th graders or whoever's reading this book, so I refuse to even engage with the content of this question. I prefer to phrase it in the Spivak way, which is almost identical except for the fact that there's no actual numbers here. We just phrase it abstractly. So Spivak does not condescend to you. He simply asks you to prove that of all rectangles with fixed perimeter, right? So this fixed perimeter assumption is the analog of the statement that Cody has only 40 feet of fencing, right? Having only 40 feet of fencing to build a fence means that your perimeter has to be 40, right? So then Spivak says, all right, fine, if the perimeter is fixed to be some number, we want to get the biggest area, and you want to prove that's a square rather than something else. So whatever. I mean, that tells you that the maximum area Cody could have enclosed in this problem is whatever area he would get by building a square that's 10 feet on a side. But instead of doing the, Baroness, Puffelstein, whatever bullshit, we'll just prove this. So, okay. How do you think we should start to do this sort of optimization style problem about maximizing the area?
I guess begin referring to the formula for area of a rectangle.
Okay.
Don't see anywhere else to start. That's just going to be x times, L times W.
Length times width. Okay. Good. So that's what we want to maximize. Now we just need to take into account the fact that the perimeter is fixed, right? So what is the perimeter of a rectangle with length L and width W?
2L plus 2W equals some P.
Yeah, I'll call it capital P for perimeter. Okay. Good. So the first thing is, well, we're trying to find a maximum. So, we're trying to maximize this function as we change one of the variables. Unfortunately, the way we've written this involves two variables, right? Length and width. So somehow we need to substitute in for one of those variables, either length or width, in terms of a constant, right? We want to get rid of one of the variables and trade it for a constant. But we know the perimeter is a constant because by assumption it's fixed. So what should I do to eliminate one of these two variables in favor of the constant capital P?
I don't know if it's relevant to the question, but I'm thinking that we could somehow algebraically manipulate the right equation to get something in terms of, if we want to remove L, we put it in terms of W.
Yeah, good. So say we do that. If we manipulate this equation to get L in terms of P, what do we get after solving?
It's going to be L equals P minus 2W over L.
P minus 2W over 2, right?
Right. Yeah, I don't know how I did that.
Yeah, no problem. Okay, good. So that's L. Let's put that into A, which is good because now A is only a function of one variable, now W, because we're getting rid of L, right? So A as a function of W is L, which is this junk. I'm going to split the fraction because, I want to. So that's P minus W. That's the L. That's all times W. Or perhaps more conveniently, that's going to be the constant P over 2 times W minus W squared. So I'm just rewriting that. Okay, good. So we're in good shape now. We have a function for the area, and now we want to maximize that function, right? We want to find the case with the greatest area. So what should I do to maximize this function A of W in terms of W?
Do we want to find some point where negative W squared equals W?
Let's see.
Or is that not quite? I don't know if we would do that, or if it's even a good idea.
Yeah, I don't think that would work, as negative w squared equals w would only be satisfied if negative w equals 1, which is true where w equals minus 1, or where w equals 0, right? But we're assuming these are, w measures a length, and lengths are always non-negative, right? So, I mean, if you prefer, maybe it's easier to just think of this abstractly. Don't think of this as an area. Just think of this as a function f of x, which is some constant, p over 2 is some constant cx minus x squared. And I say, find the maximum value of f on some interval. What's the interval? Well, w is a length, so it can't be negative because it measures a length. The smallest it could be is 0 if this thing is like a point, but it can go up to infinity. So if I just handed you this problem and said, find the largest value that the function cx minus x squared takes on this interval, how would you attack that problem?
Take the derivative.
Yeah, good. There's only 3 points where the max could be, right? It's either at the endpoint, or at a place where the derivative is 0, or at a place where the derivative is undefined, but this is a polynomial, so there's none of that. Okay, so good. How do I take the derivative of a of w?
You see that a prime of w is going to be t over 2 minus 2w.
Very good. Okay, so where's that 0? For what value of w?
And this is going to be 0 for... We can go through algebraically. Right. We can move the p over 2 to the right side and see that negative 2w equals negative p over 2. And then divide each side by negative 2.
Okay, so that gives what? W equals minus p over 2 over minus 2. Minus is cancelled, so it's what? P over 4? Is that right?
Right.
Okay, so I think we know what shape this is, because if we have a rectangle, I'm going to pointedly draw it as a rectangle for the moment, but then we'll see that's really not the way to do it. If the width, which is the shorter dimension, is a quarter the perimeter, that means these two are both p over 4. But we know that, the length is p over 2, I'll just rewrite this. The length is p over 2 minus w. But if w is p over 4, that means the length is also p over 4, right? So apparently, with this solution you've just told me, w equals p over 4, we get a rectangle where all 4 sides have the same length. And we have another word for that. It's called a square. Right?
Wow.
Okay, good. So we have solved the problem. If you prefer to think of it in the bullshit way, this is to say that if you have a pet goat and want to build a rectangular grazing area for her, you should build it in the shape of a square. Perhaps more abstractly, we've proven that if you have a fixed perimeter and want to maximize the area of a rectangle, the maximal area is achieved on the square. Okay, questions about this?
If I ever get a goat, that is its name.
Baroness Regina von Puffelstein. I hate it. I feel like this would be a better name for a pony than a goat, but whatever. Jesus.
Well, equines aren't fluffy.
Aren't puffy? Yeah. I didn't think of Puffelstein as referring to a texture. I just thought it was like supposed to evoke like this 18th century Germany or something. I don't know. Whatever. Other thoughts?
No thoughts.
I wanted to make another slide. Well, first let me recap that solution. So, indeed, fix the perimeter fix the perimeter P. Then, if the length is L and the width is W, this is the formula you gave me. You can solve for, I think you solve for L instead of W, but whatever. Write the area in terms of the one free parameter, which I called L. To maximize, you take the derivative, set it to equal to 0. So, in fact, in my solution, I took the second derivative to prove that it was a max instead of a min. But I don't think that's really necessary. You can kind of tell that it has to be a max rather than a min, because you could have gotten the minimum by taking a very, very skinny, right? You could have made a skinny rectangle so the area is very close to 0, right? So we kind of knew just on physical grounds it could not have been a minimum. It had to be a maximum, but I just checked that in my solution. Anyway, so where the derivative is 0, we get the length is p over 4, but by definition of square, L equals p over 4 is a square. Okay, good. That's what we just saw. But okay, I wanted to make another slide solving this in a different way, because we're going to start talking about symmetry on Tuesday. So here is a spooky but totally rigorous way to solve this problem that involves no calculus whatsoever. So, claim the area is maximized for a square. And we can prove this by contradiction. Here's the proof. So we're going to suppose that the global maximum for the area, so the global max is achieved for a rectangle, so L and W are not equal, and let the dimensions, the length and width, with, say, length L and then width W. Okay, so we're going to suppose by way of contradiction it's not a square. Now I'm going to draw it. So here's the non-square rectangle that we are supposing is the global maximum of the area function. Right, so here's L, and here's W. Now here's the key step. Rotate the plane by 90 degrees. So we've seen in the matrices unit, well, I don't know why I'm saying 90 degrees. I really mean pi over 2. We've seen in the matrices unit that you can cook up a matrix, which is, I guess, cosine of pi over 2 is 0, minus sine of pi over 2 is minus 1, 1, 0, whatever. So you can find a matrix that acts on the entire plane to rotate every point by 90 degrees counterclockwise about the origin. So if you act on the entire plane with that rotation, I don't know, I'll call it r sub pi over 2 to use the notation that we had in the matrices unit. This new rotated plane now contains a rectangle that looks like this, right? So again, this is L and this is W, but now they've been kind of reversed, right? Now, like, the horizontal dimension of this rectangle is W and the vertical direction or dimension is L instead of the other way around. Now, we've proven in the matrices unit that acting with a transformation changes areas by a factor which is equal to the determinant of the matrix. Right? Remember, determinant tells you how much areas are rescaled. The determinant of this matrix is 1, right? It's 0 times 0 minus 1 times 1, which gives you plus 1. So this matrix does not change areas. We didn't really need to use determinants to prove that. You could have just appealed to intuition, right? If you rotate your head by 90 degrees, it's not changing the areas of any figures you're looking at. It's an invariant under rotation. So the punchline is that this rectangle is also a maximum for the area function, a global maximum. So now we have an interesting fact that apparently, I don't know why I'm scrolling down because that's not giving me any more room to write with. So apparently, based on this argument that if you could rotate the plane by 90 degrees, you have another global maximum, this means that A is maximized for both a rectangle with kind of vertical, a horizontal dimension L and vertical dimension W, but also the alternative is one with horizontal dimension L and vertical dimension, horizontal dimension W and vertical dimension L. because if you rotate it, this is apparently still a global maximum because area does not change. So the punchline of this argument is that if length L and width W gives you a global max for area, you can simply rotate the plane and then see that apparently also length W and width L, the reverse, is also a global maximum. But that's a little weird because global max is unique, right? Global max, there can only be one, right? Global max is the highest value of area achieved for all possible values of L and W. So the only way you can achieve that global maximum with two different pairs, L comma W and W comma L, is if that maximum actually has these two equal. Right? So the only way this can be true is if L equals W, so it must be a square. Right? Anyway, okay, so kind of I made that argument longer than it needs to be. Here's the short version. To see that it had to be a square, just think about a rectangle, rotate it, and then see that the rotation exchanges the length and width. So if the length and width were different, apparently the solution with L and W would give rise to a second solution with L and W reversed, W and L. However, we know there's only one unique pair, L and W, which solves this problem. So the only way the problem can have two different solutions is if they're equal, and the only way these two can be equal is if L equals W. That's the punchline. Okay, so this is very slick because it involved no calculus whatsoever. It just involved thinking hard. So this is an example of what's often called a symmetry argument. So symmetry arguments are almost spooky. They always seem to use very little information. They're very slick and very powerful and allow you to prove something which would otherwise take a lot of calculation without writing any numbers down. All we had to know is that here the symmetry is rotation of the plane, and that symmetry leaves the area fixed, right? That was enough to prove the claim. So we'll see much more about symmetry arguments and why they simplify questions in chemistry as we prepare our talk. But okay, now I've been already talking too long, so thoughts on the symmetry argument?
I do not have any thoughts.
Okay, but you find the argument convincing, I hope.
Yes.
Good, okay. Symmetry is very powerful. All right. Back to the regularly scheduled programming then. All right, we can go faster through this one. All right, so similar to the last problem, another extremization problem. We want to prove that the sum of some positive number and that number's reciprocal is always at least 2. So I claim the goal will be to write down some function which represents the sum of a positive number and its reciprocal, find, the minimum, we want to minimize that function, find the smallest, and show that that minimum is at least as big as 2. So the function never goes smaller than 2. What should I do to do that?
So I guess put this into equation form and see that S equals x plus x to the power of -1.
Good. Okay. So how do we minimize S? We just put in the assumption again since it's a positive number. I just want to remind us x is positive. But okay, so how do we minimize S then?
Is the answer plain and I'm not seeing it?
Well, no, I mean, how do you find, for any function, how do you find where the max and min occur?
We derive.
Differentiate, not derive, but yes.
Right.
Yeah, good. Okay, so
I figure out the difference between those.
So what is S prime of x?
This is going to be equal to 1 plus -1x to the power of negative.
X to the power -2, you said? Okay. Good. Okay. What should I do with this expression then?
I don't quite know.
Well, we're trying to find the minimum, right? So minimum occurs in three places. It occurs where f prime equals 0, or at an endpoint, or where the derivative is undefined, right? So there's only three possibilities. Now there's no endpoints because this is an open interval, right? This is the interval 0, comma infinity, so we know it can't be this one. The only place where this is undefined is at x equals 0, but that is already excluded from our domain, so there's none of case 3. So it looks like the minimum can only occur where the derivative is 0, right?
All right.
Good, so what do I do?
So we see that 0 equals 1 plus -1 x to the power of -2, or -1 equals -1 x to the power of -2.
Okay, what value of x is that?
Something that results in x to the power of -2 being 1.
Good, so 1 over x squared equals 1. This has two solutions. What are they?
I believe -1. No.
Yeah, -1 works. 1 over -1 squared is 1 over 1. So
Right. Yeah, -1 and 1. I don't know. I hesitated.
no worries. Okay, so I think we can rule out -1 because we stipulated that it was a positive number. Okay, sure. So we found that the derivative vanishes at x equals 1. So this is either a local max or a local min. How do we decide whether it's, well, I say local, but actually we've ruled out the other two possibilities. So this is either a global max or a global min. So how do we decide whether x equals 1 is the global max or the global min?
Well, my first idea is figuring out somehow if this function is, what's the proper name? Always increasing? I can't quite remember.
Ah, okay. Increasing or decreasing. Okay, so yeah, I mean, sure, that's one way to do it. So let's just try to get some intuition. Is this function increasing or decreasing? Well, let's think. If I plug in a very small number, like 1 over 1,000, well, I get 1 over 1,000 plus 1,000. So that's very close to 1,000. It's 1,000 plus a small number. So it seems like this function is pretty big when you give it a small input. What else? What if x is very large? So if I plug in, instead of 1 over 1,000, if I plug in x equals 1,000, well, I get the same thing. I get 1,000 plus 1 over 1,000, which is about 1,000. So it seems like this function gets very large. I'm just going to plot it. Fuck. The function s apparently gets very large near 0, and then gets very large near infinity. So this intuitive argument seems to suggest that what we found should be a minimum, right? Since this seems to be smaller than its values to the left and right. Okay. That's in fact correct. It's not a proof, but that is in fact the answer, that this function takes on its smallest value when x equals 1. So what is the value of s of x when x equals 1?
It is 2.
Good, it is 2. So if we believe that that is indeed the global minimum, then we have proven that the function s of x is always greater than or equal to 2, which is what we wanted to do. Right? The sum of a positive number and its reciprocal is always at least 2. Okay, if we wanted to see that a bit more carefully, we could have, in addition to taking the first derivative, which you told me was 1 minus, or I think you said 1 plus minus 1x to the minus 2, which is what you said, we could have also taken the second derivative. Why does the second derivative help us? Because we proved a few minutes ago that if f prime is 0 and f double prime is positive, then f has a local minimum at a. And indeed, in our case, it was also a global minimum at A. So we've just today discovered the second derivative test that tells us whether a place where the first derivative vanishes is a max or a min. Right, so we could have used that, if you like, to take the second derivative of the function, which I call f and you called s, and find that that thing is positive at x equals 1. So if this thing is positive at x equals 1, it must be a local minimum, and there are no points of type 2 or of type 3, no endpoints or no points where the derivative is undefined, so it must be the global minimum. So indeed, if you add any positive number in its reciprocal, you are guaranteed to always get something at least 2. Good. Okay, thoughts on this?
I do not have any thoughts.
Very nice. Okay. A slightly more physical example. So suppose we have a spring. So this is an example of what's called damped harmonic motion. So I'll put time on the x-axis and put the position of the spring on the y-axis. So the spring starts moving at time 0, and it's going to oscillate away from its equilibrium position. So if you think this is like stretching a spring which is submerged in molasses or something, right? So you stretch the spring and let go, and it starts to return, it's stretched, so it wants to get shorter, but it's in molasses, so it's kind of slowing down as well because the molasses is kind of retarding its motion. So you start at time 0, and if we plug in time 0 to the function I've given down here, e to the 0 is 1, and cosine of 0 is 1. So it starts at time 0 at position 1, and the point is that this thing is going to, that's probably a bad color, but this thing is going to execute some kind of motion like this, where it's oscillating, but it's also kind of settling down as it oscillates because the molasses is slowing it down. So asymptotically it comes to rest. But anyway, okay, so that's what this thing looks like. And the question is to find the maximum and minimum values of its position. So if it oscillates in this way, y is e to the minus t cosine of t. What are the largest and smallest values of y it achieves on this, time in 0 to infinity? What are the max and min on that interval?
So I believe that we can just run through the cases. First we see thinking. Okay, first we are going to take the derivative because I know that we're going to use it.
Okay, so what's y prime?
So y prime of t is going to be, by the product rule first, we are going to have, and subsequently by the chain rule, e to the power of negative t times negative t times cosine of time.
Minus
Plus.
1, not minus t, right? We're taking the derivative with respect to time. The derivative of minus x is minus 1, right? Good.
And that is times cosine of time.
Good, okay. Second piece.
And that is going to be plus e to the power of negative t. Did I miss my button? Negative sine of t.
Ah, good, okay, yeah. Sorry, you cut out there.
Yeah.
Good, okay, so where is this 0? So I'm going to set this equal to 0, and I think we can cancel the e to the minus t. Since if this whole thing is equal to 0, we just divide by e to the minus t. So when we divide, we get the equation, let's see, minus cosine t minus sine t, is that right? Equals 0. Okay, so is this right? Yeah, we have a minus sign here. Yeah, I think that's right. So that's the same as saying cosine t equals negative sine of t. Or I guess we could even, if you prefer, divide by cosine of t, because sine over cosine is called tangent. So this means tangent of t is minus 1. So do you remember what sort of angles have the property that their tangent is minus 1? maybe it helps to look at the unit circle.
Quite remember.
You don't remember? Okay, so where are the points where the x value is negative of the sign value? So I think, for instance, this guy probably works because this guy has the y value as being, some positive number, and the x value being the negative of that same number. So this is supposed to be 45 degrees away from 180 degrees, or if you prefer pi over 4 away from pi. So what is this angle that I've drawn in radians?
A lot of buttons messed up there. Okay then, 3 pi over 2.
3 pi over 4, right? 3 pi over 2 is down here, right? This is 3 pi over 2. Pi over 2 is 90 degrees, so 3 pi over 2 is 90 plus 90 plus 90 is 270. So 3 pi over 2 is down here. Right?
You can add. Unlike me.
Barely. Okay. Good. Okay, so as you say, this happens at t equals 3 pi over 4. But of course, we can add 2 pi to this, and the tangent will stay the same, right? Or in fact, we could just add pi to this. Don't even have to add 2 pi, because as we've proven a while back, the tangent function has period pi. Why is that true? Well, because if I'm over here at 3 pi over 4, and I find that the x value and y value are related by a minus 1, then I have another solution down here. Because here, now the x value is positive, but the y value is negative. So I can get infinitely many solutions by continually adding pi to this value. So if I add pi to this, I get 7 pi over 4. If I add pi again, 7 plus 4 is 11, so 11 pi over 4, dot, dot, dot. Okay. So I get a lot of solutions. Does that make sense physically? Well, yeah. We're finding places where the velocity of the spring is 0, which means it's turning around. It's changing direction. Why should it change direction infinitely many times? Well, alright, it changes directions down here, because the tangent line is horizontal. It changes directions again up here. Tangent line is horizontal. Over here, it's going to change directions again. So it changes directions infinitely many times. That's fine. That makes total sense. Okay, so that's the type 1. Are there any endpoints or places where the derivative is undefined?
The singular endpoint would be when x equals 0, and therefore y equals 1.
Good. Alright, what about type 3?
And hopefully that we will have to worry about negative time.
Mm-hmm. Yeah, ignore negative time.
I do not believe that there's any points where this is undefined.
Good, yes, this is defined everywhere. Okay. Alright, so now all we have to do is ask the question, among all of these points, either the points where time is one of these, strange fractions involving pi, or where time equals 0 and y equals 1, can you see either intuitively or just by plugging these numbers into the function and noticing that, e to the power minus t gets very small as the thing inside the exponential, the power, the minus t, these are getting larger and larger. That means this thing is getting smaller and smaller. So can you kind of guess, based on that intuition, where the global max and global min occur?
So the global maximum occurs at x equals 0, and global minimum occurs at x equals 3 pi over 4.
Perfect. Yes. Good. So it's precisely because of this damping, right? So if you pull the spring up 1 meter away from where it wants to be and let go, but it's in molasses, then it's going to come down less than 1 meter in the opposite direction. Then it's come down even smaller than that, and this gets smaller and smaller and smaller. So indeed, all of these higher critical points at later times are going to be closer to the origin than the first two. So we just have to look at the first two, and of the first two, it's fairly obvious that the position y equals 1 is the global max, and the position, whatever this is, y equals e to the minus 3 pi over 4 times, what's this? Negative root 2 over 2 or something, minus 1 over root 2, whatever that is. That's going to be the global min. Good, so that is indeed correct. This is a problem taken from my, when the fuck did I take this? Sophomore fall physics major class, 803. This is a classic 803 question where you deal with these damped oscillations. But anyway, questions on this?
I have no question.
Okay. Let's just run through that again. As you say, the derivative is defined everywhere, so there's nobody in type 3. The only endpoint is times 0, which had value y equals 1. Took the derivative, which I just kind of factored out the e to the minus t, vanishes where the tangent is minus 1, which it looks like all of these points, and intuitively, well, not just intuitively, it's just true that of those, the global max occurs at times 0 and the global min is at the first critical point. Good, okay, another pretty maximum problem. Alright, so the Act 2 is a different topic on root finding, but before we switch topics, any last thoughts on optimization, maxima, minima, etc.?
I have no thoughts.
I do not think anything. My brain is turned off. Okay. No, that's fine. Yeah, there's fewer challenges here, so this will be somewhat more expository, but that's just because, I don't know, I think it's hard to ask good questions about this. But first, some motivation. So why, when I first learned about this, I asked, why do we care about root finding at all? So here's my answer to the question of why root finding is important. Often in math, your problem or question boils down to solving some equation, right? In an Algebra 2 class, you might be asked something like, find a place where x squared plus 2x plus 1 equals 0 over the complex numbers. So this is solving an equation where f of x is this quadratic and g of x equals 0. So that's already in root finding form. Maybe later you'd find an equation where cosine of t equals minus sine of t. That was something we just did moments ago in that spring example. So in this case, the right side is non-zero. But in any case, almost all of these sort of algebraic questions boil down to find some value of your variable where a certain expression on the left side, say f of x, is equal to another expression on the right side, say g of x. That's a lot of problems. I mean, if you ask someone who just took an algebra class, they might think that's all of math. I mean, you know better now. There's, much more interesting questions about, proving, things about set equality and much more abstract ideas. But I don't know, to the average 8th grader who just took algebra, they think this is all of math, right? You just solve equations. So one example, which we don't know how to solve at the moment with our toolkit, is find a value of x where e to the power x is the same as sine of x, right? That seems very hard. We don't know how to do that. I mean, you can't just take a log of both sides because then you would have x equals log of sine of x, and we don't know how to solve that because now x appears on both sides, whatever. The argument I would like to make to you is that if you accept that this first type of problem is important, then you should naturally accept that finding a root is an equally important problem. What is finding a root? Finding a root question is a problem of the form, find a value of x where some function h of x equals 0. Right? As we discussed recently, this is, root equals place where thing equals 0. Right? So a problem of this form is asking you to find a value of the independent variable where some function equals 0. Why are these the same thing? I claim that any question of the form, find a value of x which solves an equation, is totally equivalent to some question of the form, find a root of this function, because you can simply subtract the right side from both sides, right? So this problem, find a value of x where f of x equals g of x, is exactly the same as finding a value of x where f of x minus g of x equals 0. And then we can simply pick a new function h, which is equal to f of x minus g of x. Right, it's a simple trick, but we've seen this a lot of times. Like there was a mean value theorem question recently where you were finding a place where something about f equals g, and the idea was to subtract and have f minus g on the left and use a theorem where h equals 0, blah, blah, blah. Damn it. So anyway, the point of this is that root finding is at least as general as solving equations. Any question about solving equations can be rephrased as a question about finding roots. So for example, if you want to solve the equation e to the x equals sine x, you might as well ask the question, for what value of x is this new thing, e to the power x minus sine of x, equal to 0? It's the same question. So this is why root finding is important, in my opinion. Okay, thoughts on this or on the motivation?
I do not have any thoughts.
Okay, good. So if we're on board with the idea that root finding is important, let's think about how we would do it. Right, so there should be a benchmark. There should be some simple way to find the root of some equation, like find a value of x where e to the x minus sine x equals 0. We should have some way of doing that which is just stupid, and we'll try to do something smarter than that. So what's the stupid way? The stupid way is bisection. So here's the idea of bisection. You find some interval where the function changes sign, and I'll draw this again on the next slide, but if you can find some interval and you know that the function whose root you are trying to find changes sign on that interval, then by the intermediate value theorem, which guarantees that you hit everything in between those two endpoints, if it's positive here and it's negative here, you're guaranteed that there's a root somewhere on the interval, but you don't know where. Well, how do you find where? You just do the dumbest possible thing. You guess halfway between the two endpoints. And you know if it's positive on the left and it's negative on the right, and you compute its value halfway in between, maybe halfway is here. You compute the value and say it's negative. Well, alright, so if it's negative, then you just restrict your interval. Now you know it's still positive on the left endpoint, and you know it's negative at that value you just computed. So you just repeat this process. Let's guess halfway in between again. So you'd guess again and get something like here. And now it's positive. Okay, so now I cut my interval again. Now this is the new interval, and it keeps getting smaller and smaller. You keep going halfway in between and cutting the interval either in half to the left or in half to the right until you get a tighter and tighter interval around the root. And in practical applications, maybe you need accuracy to 3 decimal places, so you stop when the size of your interval is smaller than 3 decimal places, 10 to the minus 3. So that's the bisection search. It's totally the simplest thing you would think of. Here's the picture. So it's the same thing I just drew. You know the function is positive at some point a1, and it's negative at some point b1. So you try halfway in between, cut it in half, and then say, okay, well, we tried halfway in between and it was negative, so now we're going to cut it in half and try halfway in between. Damn it. Halfway in between again. That one was positive, so now we cut it again, try halfway in between, positive, and so forth. So at every step, you restrict the search space, the interval you're looking at, to cut it in half again and again and again. And eventually you get an approximation to the true root. Okay, questions on bisection?
I have no questions.
Good, okay. I mean, it's also easy to implement in Python, so. Alright, now you might ask, this was a really stupid way of trying to find a root. It used no information whatsoever about the function. It just guessed halfway between the two places that you're looking at. So is there any way that we can use more information about the function to improve the performance? And this is a very common theme in optimization or numerics, is that the more information about the problem in hand you can use, the better bounds or the better approximation you can get. So suppose that in addition to knowing how the function itself behaves, we know something about its derivative. So in addition to knowing f, we can approximate or compute exactly or whatever the derivative f prime. How would you use the information about f prime to get a better guess for where the root's going to be? Well, we saw in the prologue when we were doing this special relativity stuff that there's this very nice tangent line approximation. This tangent line is a good estimate of f close to a root. So here's the idea. Suppose you have a guess, which we'll call x sub n. N is going to be an index because we're going to keep improving the guess as n gets larger. But you have this guess x sub n for where the root should be. And rather than picking some random point halfway between xn and some endpoint, you do the following. You go to the point f of x sub n on the graph of the function you're interested in, and you compute the derivative, so you know what f prime of x sub n is. Using that, you write down this tangent line approximation. F sub x is roughly f of x sub n plus f prime of x sub n times x minus x sub n. That gives you the tangent line. And then you say, to get an estimate for where the root should be next, I find where that tangent line equals 0. That's here. And I call that my next guess, x sub n plus 1. The claim is that this is a better guess for where the root should be next than just cutting, some interval in half and looking halfway in between or whatever, because that depends on how good my interval was. This thing uses more information about the function. It uses the derivative, so in general it should be better. The idea is just use the tangent line. Okay, thoughts on this?
I have no thoughts.
All right.
As is usual.
What do you say? It's useful?
I said, as is usual, I have no thoughts.
Ah, good. Eventually I'm going to start pressuring you to generate thoughts even if you don't have any. Like pretend you're sitting in a lab meeting with someone and a graduate student just presented his work from last week, and then the PI asks you, come up with some comments about this, and you have to generate thoughts on the fly. But anyway, now's not a good time for that. So here's the challenge. Let's look at the picture we had a moment ago. So I told you we knew, some point x sub n, and we knew the derivative f prime at x sub n, and we wanted to find this root, the place where the tangent line equals 0. So I will ask you now to tell me what algebra to write down to find what that new point is. So again, let f be a function and choose some point x sub n. How would you find the root of the tangent line approximation, which is in other words the place where the line approximating the curve hits 0, the root of the tangent line approximation to f near x sub n? What should I do for this?
I'm in deep thinking. I don't even know if I need to be in deep thinking right now.
Let's do the first thing. Let's not question the root. Let's just write down what is the tangent line approximation. So the tangent line approximation is something with an approximation. What's the right side of this?
The tangent line approximation is going to be difficulty thinking f of some a.
Oh, what's x sub n here? Yeah.
Well, f of xn. Yeah. F of xn plus the... Okay, this wasn't... I'm trying to remember point slope form, but I never memorized it.
Y equals y1 plus m times x minus x1. You don't even need to memorize this. You just remember that m equals y minus y1 over x minus x1. That's just what slope is, right? It's change in y over change in x. But then if you multiply both sides of that by x minus x1, it gives you this. So anyway, the point is you never need to memorize anything. You can just re-derive it all when you need it. But whatever. So, all right. So what the
So this is going to be the f prime of x plus xn.
Well, f prime is at xn, and then this thing is supposed to be the difference between x and that point.
Right.
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 Good. So this is x minus xn. All right. So that's the approximation. We want to find the root. So what do I do to find the root of this expression on the right side?
Can we move the f of x to the right side?
F of x to the right. Well, we're trying to find the root of this expression, right?
Set it equal to 0.
Yeah, good. So all we
Much
care
better.
about. Would you like to join his D&D campaign? Well, maybe later.
Oh, yes, I would with my little old Asian lady.
Good. Okay, so this is equal to 0. Now we're trying to solve for x. So let's see if you can do some algebra on your feet. So how do I solve this, the bracketed part, that the approximation equals 0? How do I solve this for x? What do I do?
I'm sorry, I was trying to comprehend the basically you but smaller going on.
Basically me. Oh, the comment. Yes, I ignored that.
What was the question? Okay, I'm not going to look at that. What was the question again?
So we're trying to solve this for x. What do I do?
Alright, so we're going to move the f of xn to the right side, and then divide each side by f prime of xn.
Okay, so you say move f of xn to the right, and then divide by f prime. Okay, so I guess I should have a minus sign here because I subtracted. Divide by this. Okay, good. So then I think there's one more step to different color. One more step when I get rid of the x sub n, but just read it off for me. So what do I get for x?
So x is going to be equal to negative f of xn over f prime of xn, all plus xn.
Good. Plus xn.
That looks really nice.
It's very pretty. Yeah, I like the symmetry of this. Thing over derivative of thing. But okay, good. Right, this is the root of the tangent line approximation. So this is the point in the picture before where, well, I shouldn't do that. This is this point x sub n plus 1, where we found the tangent line, we found the place where the tangent line equals 0. Now we've just done that with more algebra. So this is that new thing which I was before calling x sub n plus 1. So that's our new estimate for the root. Okay, good. So I will rewrite that. So indeed, you write the tangent line approximation, set it equal to 0, and solve, and you get x sub n minus f of x sub n over f prime of x sub n. And this gives you a new estimate for where the root is likely to lie. So now this suggests an algorithm because you need not stop after doing this process just once. If you want to continue improving your estimate for the root, the idea is fairly obvious. You just do the whole thing again, right? So now that you have this new estimate where you found, the tangent line approximation to where the root of the function should be, just do it again. Do the same thing where you approximate this function by its tangent line, which I've drawn very poorly, the tangent line here, and find the root of that tangent line. And as you see, we're getting closer and closer to the true root of the function f as we iterate this process over and over. So this naturally lends itself to computer science. We can write an algorithm to continually iterate this approximation and make it better and better. So here's the algorithm. Let f be a function again. Let x sub 0. We have to start with x sub n where n equals 0. X sub 0 is your initial guess for the root of the function. It's probably not right, but it's some guess. So at each step n of the algorithm, starting with n equals 0, I'm going to start loading this because my computer's very slow, but at each step n, we do something which is known as Newton's method. Sometimes the Newton-Raphson method for the two people who, contemporaneously co-discovered it. but at each step we improve the approximate root x sub n, typo, to x sub n plus 1 using the following steps. First, you approximate f near the estimate x sub n using a tangent line approximation. So you told me that a moment ago I should write f of x is approximately f of x sub n plus the derivative f prime of x sub n times x minus x sub n. Then you set this whole thing equal to 0 and solve for the place where that thing vanishes, right? So you solve for x, where this thing equals 0, and as you did a moment ago, you get x equals x sub n minus f of x sub n over f prime of x sub n. And then the idea is you just say, okay, I declare this new root to be my new guess, right? So that's the next one, x sub n plus 1. So more concretely, you would start with x0. You would do this thing, use this formula to get x1, and then you would start over and use that to get x2 and x3 and so forth. And we should now move to the animation to see what this actually looks like, which is for some reason still loading, despite the fact that I started it several seconds ago.
Nearly a minute.
Damn it. It is processing request. That's very frustrating. Here we go.
Oh no. Oh, the name loaded.
It's something. Man. Why is it so bad?
What is up with your recently? I noticed that your voice has been glitching out.
Oh, I don't know. I mean, my computer seems okay. Maybe my Wi-Fi is bad or something.
Also, I heard my voice running slow through your computer.
That's weird because I have headphones on, so there shouldn't really be any echoing.
What?
Alright, well, I clearly put the link to the .gif, and it loaded the Wikipedia page instead of the GIF itself. Oh, no, here, the GIF is coming. Here it is.
Here it goes.
For reasons which are unclear, the words function and tangent appear to be in, like, German or something down here, but here's what's happening.
Germany.
You see what's happening at each step. We're going to the guess, and then finding a tangent line approximation, and then finding where that thing vanishes. So here we're going, starting at x1, tangent line approximation, get x2, approximate this, find the root of the tangent. This one took us further away, in fact, but then we do another approximation, find this, and then do another, find where this vanishes, and this one is the true root of the function. So the idea is to continue successively approximating the function using the tangent line at each step, and hopefully get closer and closer to the actual root in a way which is faster than simply bisecting. Okay, questions on the method?
I have no questions.
Good, let's see an example. So, I mean, actually the AOPS book and many AP calculus courses ask you to actually do these sorts of problems, like by hand. I think that's kind of cruel and unusual punishment and insulting to your value as a human to ask you to like go through all of these steps with, you know, a calculator or something. So I will show some examples and then maybe ask you to implement it in Python so that a computer will do the arithmetic for you. But just as an example to see how this would actually work in practice, suppose you want to approximate the fifth root of 23 and you want to do it very accurately. So this is a similar problem to what Feynman did with the cubed root, except now we need it maybe more accurately than before, so we can't just use a tangent line. Maybe the tangent line approximation isn't good enough. And in fact, we'll see that in a moment. So the solution is that first you need to convert this question into a statement about finding a root of some function. Right, so finding the fifth root of 23 is mathematically equivalent to finding a number x, such that x raised to the power 5 equals 23, right? That's what fifth root means. Subtracting 23 from both sides means that's the same as finding a root of this other function, x to the power fifth minus 23. Right? So if we find a place where this function vanishes, then we found an approximate fifth root of 23. Okay, great. Well, we start with an initial guess, this x sub 0. I mean, I just chose this because I know that 2 to the power 5 is 32, and that's the closest fifth power that I know to 23. So we use the formula you told me a few slides ago, which is the guess x0 minus the function at the guess minus the derivative. So what is that? Well, the function at the guess is, well, the 2 raised to the power 5 is 32, minus 23 is 9, and then we need the derivative. Well, what's the derivative? F prime of x is 5x to the power 4, which means f prime at the initial guess of 2 is f prime of 2 is 5 times 16, which is 80. So you plug that in for f of 2 over f prime of 2, and you get some number. So that's what you would get with the, I guess, Feynman method of just using the tangent line once, right? It's not very good. It's not accurate to 5 decimal places. It's only accurate to 1 decimal. So that's the point of Newton's method, is that you shouldn't settle for the first approximation if you need more accuracy. You can simply iterate. So I mean, I won't go through evaluating these because you just put them in a calculator or something, but the idea is that you now use this as your new guess. So at the next step, you take that number and subtract f evaluated at that number over f prime at that number, and you get some new estimate, and then you do it again. So you take this estimate and now take that minus the function over its derivative at that new estimate to get something new. And the punchline is that this thing converges pretty quickly, because after just those 3 iterations, getting up to x sub 3, this thing is already accurate. So you could put in fifth root of 23 on a calculator, and this would be correct to 5 decimal places. So it's actually not a bad method. I mean, you might ask, why should I learn Newton's method if I could just put the fifth root of 23 into a calculator? And my answer is that the point of learning math is, not to beat a calculator, but to learn the ideas that went into the programming of the calculator, because the people who wrote the algorithms for how a calculator computes fifth roots knew about Newton's method, and they used a variant of this, which is improved, in order to actually compute these things. So at the end of the day, if you want to be able to write computer programs that can compute things very accurately and no one else has done it before, you have to know these ideas and be able to implement them or improve them on your own in order to get an answer with desired accuracy. Okay, good. Thoughts on this example?
I do not have any thoughts. I'm looking forward to banging my head against the wall.
Yeah, I'm firmly of the opinion that every young man should try to implement a root-finding algorithm at some point in his life. It's a very good character-building experience, so I think you should do that. But anyway, so to conclude today, just a couple amusing examples of Newton's method failures. So let's just go back and remind ourselves before looking at the fails. Where does this succeed? Well, if you start really close to a root, and at a place where the tangent line is pointing you in the right direction, this thing works damn well, right? If you're this close, and it gives you, as a next estimate, this xn plus 1, and you keep getting closer and closer, this thing does very well at converging to the root reasonably quickly. Where could Newton's method go wrong is the question. So here's one place where it could go wrong. If your function looks like this, where it has some strange curving behavior, and the root that you're trying to find is in between these two kind of local max and local min situations, you could get stuck in a loop, right? So suppose your initial guess is over here, near like x equals 1, and okay, well, I'm going to find the tangent line approximation. So here's the tangent line in dotted line, the tangent line approximation to that estimate. And then I find the root of that tangent line, and I go back over here to -1. All right, fine. Take the tangent line approximation at -1. All right, it sends me back over here to +1. Interesting. Okay, well, I better go to the the function at +1 and find the tangent line approximation again. And as you can see, you go into a loop forever. I find something very amusing about this. I'm imagining like a small dog chasing its tail forever and ever. I don't know why I'm anthropomorphizing Newton's method in this way, but the point is I find it quite adorable that this thing can just run around in circles forever and it will never realize that the root is halfway between the 2 points that it's running around. So this is one way it could fail, is the Newton's method dog just simply chases its tail forever because you picked an initial point where the tangent line is unrepresentative. That's just one example. There's many other ways that this could fail. So a similar example, well, this is really a rehash of what we saw a moment ago, this sort of oscillating where there's local maxes and mins and you run around and chase your tail forever. Another more common and much more serious problem is if your estimate sends you to a place where the tangent line is almost horizontal. Right, so suppose I start with x0 here, and alright, that's fine, that's getting me in the direction of the root, so I go over here. The root I want is this thing. And then I find the tangent line approximation around this point, and oh god, that thing is very close to horizontal, so the line is not very steep at all. Now I try to find where this thing is going to hit 0, and it sends me way over here, way off even the axes, right? So it sends me to something which is way over here, and now I'm very far away from the root. So this thing sent me on a wild goose chase. It's nowhere near the root. That's terrible. Another problem is this sort of divergent behavior where, the root I want is over here, and I started over here, but because something strange happens between my starting place and the root, I was too far away, so the function's actually taking me further and further away with each time step, so I'm really never getting closer, and I get kind of screwed up. And a similar example, which is like the singular case, but kind of in the vertical rather than horizontal directions, is I start with an estimate which is reasonably close to the root, gets sent over here, which is not a great direction, but it's in the right direction. But unfortunately, the function gets very large, right? So I try to find the tangent line approximation, and my computer blows up because I try to create a number which is larger than the amount of RAM that I have because this thing gets really big. So this is an overflow error, numerical overflow. So all of these happen. I mean, I've personally mostly had problems with this, the singularities, but the others do happen apparently. So the point is that Newton's method by itself is not something that real people use to solve real problems. If you look at a root finding method in any Python library, like say NumPy or SciPy, all of them have root finding methods which are improvements of Newton. So they're similar to Newton's methods, but they have extra smart things built in. Like if I run around in circles for 5 cycles or something, I'm probably not getting anywhere. I should do something different. So there's some like if-else logic that prevents the local minima. Or, if I do an approximation and get a tangent line slope which is, less than, I don't know, 0.1 in absolute value, so it's a very small, not steep slope, maybe you put in some if-else logic that says, all right, that's probably not a very good estimate. Don't use that number. Do something else, right? So anyway, the punchline is that if you're a computer scientist trying to implement this, you should be aware of the things that could go wrong and put in either different strategies or some logic or something so that, if you're writing some high-frequency trading strategy, you shouldn't have your program crash in the middle of the night because there was some numerical overflow error or something, some singularity happened and, your computer barfed and stopped trading and you needed one of the programmers to wake up and trade out of all of your positions or something. But anyway.
Are you speaking from experience?
It only happened once, and Chris didn't mind. Anyway, good. You will wrestle with this, as you say, when you implement some root finding stuff.
Lovely.
All right, good. That is all I have for today. So, remaining thoughts or comments?
That was almost exactly 2 hours. It's just that we started later because I didn't realize you were ready. I was playing Half-Life.
Now, Half-Life is probably more useful to you than my rambling, so I am not offended.
I disagree.
Oh, well, we shall see. Okay, good. I will
Your
leave.
Wi-Fi. All right.
Ciao, ciao.